So you guys can see these slides on your screen, right?
Yep.
Yeah, there is.
Yeah.
Yes.
Good, thanks. So today we will be focusing our attention on geometric dimensioning and tolerancing. We just started a little bit about the use of this GD&T symbols in the drawing and specifications in the last lecture, and we discussed that why coordinate dimensioning, what are the pitfalls of the coordinate dimensioning is. So when we say coordinate dimensioning, it basically means that we are specifying only the dimensions in the drawing, engineering drawing, with plus minus tolerances at maximum, but we have little control over the form and orientation of the part that is going to be fabricated. And in order to address this issue, as you are seeing here, that don't have the first part, the figure here basically shows that it is not properly oriented. Basically, you have the base of this plate, which is resting on a surface plate, which is highly polished surface and has almost perpendicular form, and this is basically used as a gauge surface or basically a test bed to basically measure the form and orientation of the part that is getting fabricated. And you can see that the orientation is not perpendicular of this, I mean this side or this surface is not perpendicular to the bottom surface, and the orientation is missing. The orientation control is missing in this figure. And similarly in this figure, even if throughout the length you can have the thicknesses as per the drawing, but it is truly not in the form because there is some curvature out there, and it may be possible that that curvature is coming because a raw material that was used has a specific curvature, was not properly flat, or when the process of fabrication started it was not properly the top and bottom surface was not properly milled. So there may be a possibility that the form of the product or the part that you are going to get out of fabrication will not be controlled if the specifications, if the drawing has not called for explicit GD&T based specification. So in order to control this type of issues that may interfere with the functionality of the part, we basically use geometric dimensioning and tolerancing. So we covered this slide in the last lecture, where we discussed that there are specific specification standards, which is given by ASME by 14.5 2009 standard, that provides a comprehensive set of symbols, rules, and definitions for not only the defining the theoretically perfect geometry, but also to allow variation in size, location, orientation, and form. So this is the four geometric attributes for any feature that are there that can be controlled. One is called size, location, orientation, and form. And these are the four attributes that we are going to see how GD&T will help us to provide control on the size or the location, the orientation, and form. How GD&T is going to help us to control or provide allowable variation um, in the drawing. Now, before we actually go and further and discuss about it, uh, let me ask you guys that why do you think this variation is required? Why do you think that we need some sort of a variation in size? When I said that the point number B in here says it defines, the standard defines allowable variation in size, location, orientation, and form. So is it really required, or if it is required, why it is required? Do you uh, would like to guess or basically try to think about that aspect, that why that control or that variation is required? Why?
Mainly be for like reproduction and manufacturing in the future, so you don't have to have the engineer explain it to anyone who's either working with the part, manufacturing the part, or trying to reproduce the part later.
Yeah, I that's true. That is basically going to be the I mean that perfectly explains the need or necessity of a clear set of guidelines in the engineering drawing, so that the engineer does not need to communicate that information to the shop floor people every time the part needs to be fabricated and so on. So we need to have a clear set of guidelines in the drawing. I agree with that. But what I'm asking here that, for example, what I mean by here, if you look at the third figure here, you see that the surface is not perfectly perpendicular. There is slightly a small offset, and we are allowing that offset, even if by small amount, but we are allowing that offset from perpendicularity. Why would a designer would tolerate that sort of misalignment from the perpendicularity?
Isn't it just like your allowable tolerances that you, so even if there's that small mistake, your part is still fully functional, or yeah, it's still within the range where it will function normally, or it will fit
Yes.
properly to wherever you like whatever your the component is for.
Yeah, that's true. So that's correct. Line of thinking that, yeah, the designer would basically allow the mismatch or misalignment or variation in the uh, size or perfect form and perfect orientation, uh, as long as the fabricated part is functional. It is able to perform its desired function. So that is one line of reasoning or one thought process here. Any other thought process from you guys?
Those tolerances are in place so that in the event that the part is part of a larger assembly, that all the parts still work together without, a waste of large material because of the tolerances varying out of spec.
Yeah, that's perfect. That is almost going along the same line of reasoning as the previous student has said, that we want to make it functional and it should properly assembled in a large assembly with with the tolerances specified. So yeah, so you are basically uh, going in the same direction or providing the same, almost similar reasoning. So that is true. That is perfectly the one of the reason that is provided. But is there any other
Professor,
thing?
can you save money on the manufacturing?
Yes, exactly. So basically, this all this uh, variation or allowable variation in the size, location, orientation, form is provided just for making sure that the manufacturing also, or the part that is getting manufactured, is within a specified or is within a certain cost limit. So it basically it is able to get fabricated within a specified budget. So that you, if you would like to have a perfect form, perfect perpendicularity, perfect orientation, and with a very tight tolerances, what will happen? It would enormous amount of restraint on the manufacturer to fabricate it first, and second is it is also very difficult to inspect. So if you have very tight tolerances, perfect, uh, then what would happen that it will cause a large amount of time to inspect them for quality control. It will require very much precise machining and fabrication process. So it will unnecessarily increase the cost of the manufacturing. And to prevent that, what designer has to do is to provide as much tolerances and as much flexibility for the manufacturer, such that the part which is designed is also manufacturable, and once a part actually gets fabricated, it is also operational or it is functional. So basically the designer has to have a trade-off between the functionality of the um, parts that are getting fabricated and making sure that the manufacturing cost and the quality control cost, because of the inspection of the dimensions and other details, are not exorbitantly very high. So to make sure that the part is also manufacturable and is within the specific budget, we also have to make sure that it has the necessary tolerances, not only tolerances but also necessary tolerances in the form and orientation control. Do you see what I'm saying, guys? Yeah.
Yeah, it
Yeah,
makes
that
sense.
makes
The
sense.
more precise,
Yeah.
the more expensive.
They're more precise, more expensive, basically. And when I say more expensive, the reason for more expensive is that you require very precise machining and you require very fine quality control. So you have to make sure that the part that is getting fabricated is also, you have to spend a lot of time to inspect it, that it is within the tighter tolerances and tighter restrictions that you are providing in the drawing. So the more the tolerances, more the specifications you are providing in the drawing, more controls you're providing in the drawing, more time it will require to fabricate it. Versus if you provide a loose tolerance in the sense that it is still functional, then it will give more flexibility to the manufacturer to fabricate it at a quick or less turn. It will have a quick turnaround time for that part. Are you guys able to see what I'm trying to say here?
Yes.
Yes.
Great. Any questions so far? Okay, so some of the things that we discussed as well about how to distinguish between size and location dimensions. So, okay, in one of the chat window, there was somebody mentioning margin of error, which basically, yeah, what the tolerances are basically meant for. It is how much error you are allowing to be present in the in the dimensions of the fabricated part. So yeah, that is the purpose of the tolerances as well. Now, uh, there are two types of dimensions that we actually see in the drawing, and apart from the dimension that controls the orientation and the specification that we will see in a short while from now about controlling the form of the part, there are two types of dimensions. One is called as a feature of size or size dimension, and one is called locating dimension. And as we discussed, if any dimension that can be measured by the two opposite ends of a caliper, that is called a size dimension. That basically measures the size of the two surfaces, basically size of this rectangular block. That's what the dimension, this dimension will represent. In this this dimension basically represents a location of one surface with respect to another. So you have to basically um, yeah. So you have to basically be able to distinguish between which dimension is called a size dimension, or also known as feature of size, and which dimension is called as locating dimension. So locating dimension basically means it locates the surface with respect to another surface. So when we talk about this dimension, we require one reference surface as well, because from there we are locating it. So that is what we call as locating dimension. It requires a reference surface. Here, we basically call this dimensions feature of size just represent the size. It does not require any datum plane or datum references. So we will discuss more about datums in a short while from now as well. But here, I just want to make sure that you understand what is feature of size and what is locating dimension. So that's what basically I was mentioning here. So if you are measuring the dimensions of this cylinder or a pin and measuring diameter, and you are using two opposite ends of caliper, whether from the external or from the internal surface or internal feature, these are basically called as feature of size. And feature of size basically can have plus minus tolerances. That's all is required. You don't need anything else to uh, to distinguish or to provide information about that dimension. However, if you look at this dimension, it basically represents the location of this surface from this end, and this is basically the tolerances you are providing. But apart from on this dimension, you need to also provide the datum about from where you are measuring it, what should be the control of that datum, whether it has to be perfectly flat or not. So those type of controls you can provide on the datums as well. So these are basically the two uh, characteristic dimensions. One is called feature of size, one is cost locating feature. Okay, so having said that, so now we basically move towards what are those GD&T symbols. So as we have seen from the slides earlier, that GD&T or the standards ASME standard Y14.5 2009 standard provides a specification or provides a set of standards for controlling the four attributes of a feature of size, orientation. Those characteristics, geometric characteristics, are controlled using the symbols as you can see here. So we can control the straightness with this symbol, flatness, circularity, cylindricity, profile, angularity. So if you look at these four symbols, straightness, flatness, circularity, and cylindricity, they represents the form tolerance. It controls, these are the four symbols that will be used to control the form of a part. If you want to control the form um, of any part we fabricated, that you want to either provide the straightness or you want to control the flatness or cylindricity or circularity. So these are only the four symbols to control the form. And for controlling the form, you don't need any datum referencing. There is no need for any datum referencing. Modifier symbols, I will describe about it later. We will discuss about it. M represents maximum material condition, least material condition. L stands for least material condition. RFS stands for regardless of feature size. So we'll discuss more about it in a short while from now. But these four symbols are representing the control for the form. Similarly, these three symbols represents the control on the orientation of one surface with respect to another. Either you have a perpendicularity control, or the two surfaces are parallel to each other, or they are inclined at specific angle. And all these three symbols or three characteristics completely define the orientation of a part. Profile, we will discuss about it in a later slide, what is called a profile of a line and profile of a surface. So after the orientation, we talk about location. So if we have to control the location, how can we provide the dimension, provide the control, or provide the GD&T symbol? So one is called position control. This is the most commonly used symbol in GD&T drawing. If you see any drawing that has got GD&T symbol, you will find for sure one control which has got a position control. If there is any hole or circular shape or circular feature in that drawing, you will always find this position control, which will be a very common GD&T symbol used in any drawing. Concentricity and symmetry. It basically, again, you want to make sure that the two surfaces are concentric, or if the two planes are symmetric to each other. So you basically will use this type of symbols. And the characteristics are, the last characteristics are the runout and total runout. Circular runout basically means that how much offset you are away, offset from circularity you are allowing in your part. And total runout basically means how much offset you are allowing in the cylindricity of a part. So we will also discuss that with a specific example. So this slide just shows you the different symbols and the corresponding geometric characteristics that are controlled in the drawing using GD&T symbols. These are some more symbols which you probably have come across earlier. Basic dimension, as you can see, these are mentioned in a square bracket. Diameter, spherical diameter, these are all very common symbols. These are the symbols you probably have seen in the welding drawing. If you have seen any drawing which requires welding of the parts, you probably have come across this symbol which requires all around weld or all over welding you want. And similarly, counter bore and countersink symbols are basically mentioned using these symbols here. Spot, face, depth. This requires, this basically controls the machining or provides control on the machining of the part or fabrication of the part. If you are using some counter bore operation or you're using countersink operation, you can provide tolerances using this type of symbols. Some more symbols we will come across, we'll discuss more about that. Basically, we will only require M and L modifiers. Next. So what is maximum material condition? So before I actually read all that text, if you look at this specific drawing, it is basically representing a one square surface which has a hole in the middle, and the diameter of that is specified as 0.5 plus minus 0.1. No units are specified. So generally you need to provide the units in the drawing at the very bottom right corner, saying all the units are in millimeters or inches or whatever that unit specifications you are using. So you don't provide units right on the dimension or on the views on which you are providing the, you're showing the dimension. So here I'm showing the diameter as 0.5 plus minus 0.1. So if I ask you, what is the minimum diameter that is going to be acceptable in this case? Minimum diameter.
0.4.
0.4. And what is the maximum diameter, allowable diameter?
0.6.
0.6. Now, out of this, which one of the part will have most material in it?
The one with the 0.4 hole?
The one with the 0.4 hole, right? So basically what maximum material condition says that when you have specified a size dimension, this is, remember, this is a size dimension. It represents the diameter of a hole and represents size dimension. It has got plus minus tolerances. So whenever size dimension with this tolerancing is provided, specific tolerances are provided. So the dimension that gives or that corresponds to the maximum material in the part is known as maximum material condition. So if I look at this pin now, or basically circular projection, circular surface, which is basically representing a cross section of a pin or a cylinder, and it has got diameter 2 plus minus 0.5. Now you can see that the allowable diameter is from 1.5 to 2.5, and what condition will correspond to the maximum material in now? 2.5, right? Everybody agrees, right?
Yes.
Yes.
Yeah.
Yeah, everybody agrees with that. So maximum material condition for this drawing will corresponds to 2.5 diameter, and the maximum material condition for this will correspond to 0.4 diameter. So basically what we are saying here that we are considering a specific dimension that will give the maximum material in a specific feature, and that is what we call as maximum material condition, the condition in which a feature of size contains a maximum amount of material. So for external feature, this is an external feature, the MMC happens for the maximum value allowed with respect to with the tolerance. So maximum value allowed is 2.5. If it is an internal feature, then MMC corresponds to the smallest value allowed by the tolerance. So we are basically saying this 0.4 will be the MMC condition. Is everybody agreeing, or is everybody getting along with this description of MMC?
Yes.
Yep.
Yeah.
Great. So LMC is just exactly the opposite. Sorry, it has to be LMC, not MMC. So LMC is just directly opposite to what we discussed about the MMC. The LMC basically means, or the least material condition means, that it is the condition at which the part has got the least amount of material in it. So for example, here in this case, the least amount of material in the part would be when this is produced or fabricated. So that will be the LMC condition for this part. And here the LMC will be 1.5, because that will be the condition at which this material or this part will be having the least amount of material. Everybody is okay with that part as well? Yeah.
Can you repeat the last part, Professor?
Yeah. So what I was saying, that the least material condition means that if I have a circular cross section for a cylinder or a pin, then the least material condition will corresponds to 1.5 diameter. Basically the amount of material that will be very least, or it will be very small, will corresponds to the least material condition here.
Oh, okay, sounds good.
Yeah. So it is just exactly opposite to MMC. So here it has to be L, not M. So I will correct that as well. So in the PDF slide, it needs to be corrected. So now we actually move our discussion forward and see what is our first rule of GD&T. And I don't think there are many rules, but this is the number one rule, and it is the most important rule, which says that any part that is going to be fabricated. So here you are seeing this drawing. You have a pin here, cylindrical pin that has got a diameter of 20 plus minus 0.5. These are the size tolerances. This is size dimension. Tolerances are provided, plus minus tolerances are provided. And this is the theoretical looking perfect shape. So as we know that when we fabricate, we are going to fabricate it, we are not going to get a perfect looking cylinder. There will be some out of form or out of shape, or there will be some variation in the cross section at different lengths. So that is going to happen for any manufacturing process. Now, if that is the case, the GD&T rule says, or the number one rule says, that this
Yeah, I was wondering that. Can you guys hear me?
Yeah,
Yeah, we could hear
it
you.
was just me.
Yeah, we hear you, but we can't hear you, Professor.
Can you guys even see
Damn.
the screen?
He's still on. I thought maybe
I
he
can.
popped out, but
Yeah.
there
Oh, the
he-
screen just
There
went.
we
Yeah.
go.
Oh, there he goes.
He's probably gonna like come back in.
We're still
Yeah,
recording,
like-
so watch out.
5 to 10 minutes.
All right, GD&T rule number 1.
GD&T rule number 1, take CAD CAM.
All right, we good here?
All right, time to move
Yeah,
on
Eddie,
to
we're
rule
done.
number
Just get off.
2.
Hey, am I the host right now?
Oh, I gotta teach the class then.
Yeah, that's the rule now.
You have to share screen and share the PowerPoint.
I think we learned all we need to know. We're basically engineers now, so I think we're good.
Yeah.
He's back.
Sorry guys, my internet seems to be a bit off, so I just lost connection, and let's continue our discussion again with the slide. So is the slide up on the screen again?
Yeah. Yes.
Yep.
Yeah.
Yes.
Yeah, it's bad.
Thank you. So yeah, I was asking, sir, what is the MMC condition for this drawing? It's 20.5, right? Everybody agrees?
Yeah.
Yes.
Yeah. So what it says, the number one rule says that at 20.5 diameter, which represents a maximum material condition, you must have a perfect form. So that means any cylindrical shape or pin, as we will call it now here, this pin can be fabricated or manufactured, and it will be perfectly acceptable to the designer as long as you have this pin lying in the envelope of 20.5, let's say millimeter. So every cross section must also satisfy this drawing specification, that it have the minimum diameter is 19.5 and maximum is 20.5. So the pin diameter is between 19.5 millimeters and 20.5 millimeters at every cross section. If every cross section you measure it, you will find that the pin diameter will be between that 19.5 and 20.5, which exactly matches the specified drawing. Apart from that, if it is out of form like this, or there is some small curvature, that curvature is also acceptable as long as this pin can fit inside the envelope of 20.5. That is what we call as envelope principle or perfect form at MMC. Does it make sense to everybody so far?
Yeah.
Yes.
Great. So that is number one rule, and it basically says that if there are no GD&T symbol, in this case, if you look at the drawing, if this is a drawing that you are using for manufacturing, this drawing does not have any GD&T symbol. So in the absence of any GD&T symbol, you basically use rule number one or envelope principle, which says perfect form at MMC. That's it. So you don't need to specify any other GD&T symbol as long as you as a designer, when I say you, it basically means you as a designer are okay that if I fabricate or get a part which has perfect form at MMC, which can have some small slight curvature, but it is still functional, and it will work well in the assembly in the larger context, then that is perfectly fine. You don't need to provide any other GD&T control. You don't need to provide perpendicularity control. You don't need to provide any control on the axis of this of center axis of this hole or of this circular cross section. So you don't need to provide any other GD&T symbol, because if you provide any other symbol, that will increase the cost of the fabricated part. So in the absence of any GD&T symbol, the rule number 1 applies, which says perfect format NLC. Now, going from here, now what we will actually see that when we apply GD&T symbols, we will actually require some theoretical referencing or some origin from where the measurements will start. We call as datum. So we basically here in this slide, we will discuss more about what the datum, what do you mean by datum. So before we discuss this slide, um, any thoughts or any inputs on how do you define a datum? Or what do you mean by datum in a drawing or in any context? What does datum basically means?
Plane or spot where use it for reference.
Mm-hmm. Yeah, that's perfect definition of a datum. It's basically a plane or basically some slot or some origin from where the measurements will originate. So as I actually mentioned here also, it is basically an origin to establish the location or orientation of part features. Now, you probably have heard about datum a lot, that this is the datum that you use in the drawing. But datum, you always have to make sure that this is nothing but a theoretical context or theoretical concept, which basically means it is a theoretical plane, theoretical axis, theoretical point from which the measurements will start. Now, how that theoretical context or theoretical concept about the point, line, or plane gets translated into the actual physical objects. How do we define datum for physical objects? So if you look at this object, which is basically an L-shaped bracket, which has a hole at this surface. So this part is generally shown, the projection of, the projected faces are shown in the drawing. And one of the faces is referenced as datum feature. So datum feature is basically a non-ideal physical surface to establish a theoretical datum. So if I talk about the surface, the bottom surface of this part, and I call that as a datum, that basically means it is a datum feature. I'm talking about the bottom surface as one of the physical surface, which is obviously non-ideal, which is not theoretically flat and very smooth and no roughness. So it is basically a non-ideal. That is why I said non-ideal physical surface. It has to be a physical surface. It is not a theoretical context or concept. It is a physical surface which is used to establish the datum. Now, how to establish the datum? We place this object on a surface plate, or which is basically machine with a very precise flatness control on the flatness, or gauge pane or machine tool bed, which defines the theoretical datum from the non-ideal datum feature. So let me go back again. What I'm talking about here, we define the datum feature in the drawing, which is the bottom surface. This surface is actually sit on this simulator, datum feature simulator, which is a surface plate, a very big surface plate, which is highly polished granite surface, machine, precisely machined, and controlled. The flatness is controlled to the maximum possible level. And that is what we call as datum feature simulator. And that datum feature simulator will be used to establish the datum, because that is what we are considering, that is having the ideal surface, ideal flatness on that simulator. And we use the surface of the datum feature simulator to establish our datum from where the inspection will originate. So we talk about datum, theoretical concept, datum feature, which is the surface we are going to use a reference as a datum feature, and our surface plate or machine tool bed, whether it's chuck of the lathe or whether it is a machine tool bed of a milling machine or any other machine tool bed that we are using, that will be used as a datum feature simulator to establish the datum. Let me know if this makes sense to you guys.
Yeah, that makes sense.
Any questions from anyone from the class?
It's a little weird to understand, Professor. So pretty much the datum is just like the plane that you're working on.
Okay, let me actually see if I have got any drawing in here. Just give me a second.
Okay.
Okay, I'm just opening this slide just to make the point clear about datum. So if you look at this drawing, you basically can identify some datums here, right? And datums, as we have seen, it are basically represented by the letter symbol in this enclosed square parenthesis and uh, attached to the projected view using this fill triangle. So this is datum A, this is datum B, and it is datum C. You guys agree with that part?
Yes.
Yeah.
Yeah. Now, this is what we are calling as datum, but this is not actually a datum. This is actually a datum feature because it is representing the surface of an actual part. So when I represent this back surface of this part, that is a datum feature, which is obviously going to be not ideal. It will have some roughness and it will have some uh, contours and edges and so on. So that is called datum feature. When I put this part on a machine tool bed, the surface of the machine tool bed is a feature simulator, and that will define my theoretical datum plane from where the measurements will start. Do you, or am I able to make that clear bit?
Yeah.
If I go back to this slide, which is this one we are here. So basically the bottom surface is what we reference in the drawing as a datum, but that is not actually a datum. That is a datum feature. That datum feature is resting on the machine tool bed or the surface plate, and that surface is called as datum feature simulator. And the surface basically will be used as the datum plane from which I'm going to start different measurements. If I go to measure the height of this surface from this plane, then that will be my datum plane. Now the surface of my surface plate will be datum plane, not the surface of the part itself. Do you see what I'm saying here?
Professor, I got a question.
Yeah, go ahead.
Is it because the datum is more flat than the
Yes.
bottom surface?
Yes. So datum is, as you see, it is a more flat, basically means I am assuming it is a more flat because no object is perfectly flat, but still the surface plate or the machine tool bed is fabricated with precision machining that ensures that I am considering that surface as more flat than the part that is fabricated. So the bottom surface of this part will not be a datum. The bottom surface of the part will be resting on the surface plate, and the surface of this plate will be called as a datum plane, will be used to represent a datum plane. Does it make sense?
Yeah.
If not, just let me know and try to explain again.
So, Professor,
Yeah.
you would use your measuring device and place it on that surface and then use that measurement from there?
Yeah.
Yeah, the measurement device, which will be a gauge pin or a dial indicator, will be resting on this blade or this plate.
Okay.
So as I said that the datum, which are basically the theoretical planes, they are nothing but the surfaces of the feature simulator, which is a surface plate or maybe a machine tool bed or some other precisely machined objects or flat objects. So that will be used to construct the planes, reference planes, and the intersection of these reference planes will define the origin of the measurement. So whether it is the planes or whether it is a center axis for non-planar features, it is always remember that whenever we are considering the datum axis, it is basically the axis of the datum feature simulator. So we will discuss more about what is datum feature simulator for circular object. So we will discuss about that in a second. Okay, so next is that order of datums is important. Why? Because if we are placing this specific object in a different order, then we will see that we will have different orientation of the object itself. For example, if you see this object L-shaped bracket, this is basically placed on this bottom surface. So that is the same situation in both this both these views A and B here that we are seeing here. That is the same object, but they are arranged in a different fashion. So let me actually explain you here what we are doing. So we are first placing this object on the bottom surface. Then we are constraining this part against the back surface. And then we are constraining this part against the third datum plane, which is this. So by doing that, we are immobilizing this part, or we are constraining this part. This part cannot move anywhere else. So this cannot go in the in this Z direction or X direction or Y direction, cannot rotate anywhere. So this part is fully constrained if I put this part on the bottom face, then press it against the back face and also on the side face. So it is fully constrained. Now, if I press this part against the YZ plane first and then on the XZ plane later, then I will get this orientation. However, if I on the uh, second step, if I press this part first against the XZ plane, then you will see it requires 2 point of contact. So it will orient like this. And then I pressed it against the YZ plane, then it will require 1 point contact. It will be pressed against the YZ plane like this. So you will see the orientation of this part actually changes just because I have used different order of my datums, how I am ordering the data, whether I am doing with A and this bottom face, back face and side face, or bottom face, side face and back face. So depending on the order of datums, you will see different orientation. And if it is different orientation, then you can see that this part will be acceptable by a quality inspector if he is measuring the flatness or the dimension with respect to YZ plane. And the same part will get disqualified if you are now measuring the distance from the YZ plane and see that it is getting out of tolerances as per the specifications. So depending on how the order of the datums are specified, that is important to mention in the drawing so as to make sure that the part is getting accepted during the inspection procedure. So it basically established a precise location information so that you can get repeatable measurement, same amount of measurement. So you don't basically make the mistake of measuring one dimension at first step and measuring another dimension at the next step. So you basically want a repeatability in the measurement. And to ensure that there is a repeatability in the measurement during the inspection process, you are making sure that the order of datums are fully specified in the drawing. Any questions, guys?
Professor, so just to clarify, a datum basically is kind of like a point of reference. Is
Yes,
that yeah? Okay.
Yeah, it is just a point of reference. Yeah. Okay, so next is actual mating envelope. What is actual mating envelope means? So when a part is fabricated, I mentioned that how to define a datum feature simulator for circular object. So here you have a circular object, which is basically a pin that is having a specific out of form or curvature, as you can see here. And if I am talking about the datum of this cylindrical object in the drawing, which is basically a datum axis, how to define the datum axis? What will be the datum axis for this specific part? So as we have seen, the datums are defined with respect to the feature simulator, not with respect to the actual part. So we have to find what is the feature simulator for my circular pin. Remember, if I go back slide, so for this part, for this bracket, the datum feature simulator is the surface plate, the bottom surface plate on which it is resting, or the machine tool bed on which it is machined, or on which it is resting. cylindrical objects, the datum feature simulator is basically a slotted bracket or a plate which has got a perfect form, almost like it is precisely controlled form, a cylindrical form, which is basically called a smallest circumscribed cylinder shown in this section. So we basically use this pin and try to insert on the brackets with different holes, and we see what is the minimum cylinder, circumscribed cylinder that is required to fit the entire pin in that bracket. So that will define the feature simulator, and the axis of that hole will represent the datum axis. So center axis of the pin or by the theoretical perfect axis is basically defined by the actual mating envelope here. So the actual mating envelope basically means the smallest circumscribed cylinder that can be fitted, that will actually fit this entire pin, that will be the actual mating envelope. So similarly, if I am drilling a hole on this bracket, then the actual mating envelope will be described by a pin which is precisely controlled and whose surface are machined, perfectly, almost with a perfect precision. And the largest gauge pin we call as a gauge pin, which is used for measurement. The largest gauge pin that can fit inside the imperfect hole will be called the actual mating envelope. And that largest pin, gauge pin, will be used to define the center axis of the hole itself. So actual mating envelope are nothing but for internal features, it is the largest gauge pin. For external features, it is the smallest circumscribed cylindrical hole. So these are basically the actual mating envelope. So this basically concludes our discussion about the data. As you will see that as we move along and discuss more about the other GD&T symbols and drawings and specifications, this knowledge is very important to have about what the datums are and how the datums are established, so that you actually know how you can start the measurement of the part or how to precisely provide the information in the drawing. So this is important that we understand what is a datum, what is a datum feature, and what is datum feature simulator. Any questions so far, guys? So if not, we move to the description of the feature control frame that will describe how to provide a GD&T control in our drawing. As I mentioned, probably mentioned in the last lecture, that we use this type of rectangular frames or a rectangle with several compartments in here. So each compartment has got certain information, and we use this frame or rectangular block in the drawing to provide a GD&T control. The first compartment contains a symbol, the symbols that we have just seen a while ago, the GD&T symbol. So this symbol represents a position control. And as I have mentioned you before, this position control is quite often used in any drawings that uses GD&T symbols. So we'll discuss about that in a second, what is position control means. The first compartment contains a symbol. The second compartment contains the amount of tolerance you are providing. So that is basically the amount of tolerance. If it is just 0.25, that means the tolerance is defined by two planes which are separated by 0.25 units. Or if it is a diameter in there, that means the tolerance zone is a cylindrical tolerance zone. This modifier M basically means the tolerance is specified when the part is manufactured at maximum material condition. And then thereafter, the other compartments are representing the order of datums. Datum A, then it has to be constrained with datum B, and then the third has to be datum C. And again, a modifier here for datum you can provide if you need that. So this rectangular block, which contains the information about the GD&T symbol, the amount of tolerance zone, the ordering of datums, is what you need for specifying a control in your drawing. That is all what you need. Now, Just to read it, or what basically means, it basically means that the feature is to be positioned within a cylindrical tolerance zone of 0.25 millimeters when the pin or the part is fabricated at maximum material condition. And the ordering of datums is A, B, and C. Does it make sense to you guys?
Yes.
Professor,
Yeah.
so that means it's a hole inside of something, and then that maximum material condition meant was it the biggest diameter of it?
So one thing that often confuses us when we see this type of specification is this amount is a tolerance zone. It has nothing to do with the size of the part. So for example, if I have a cylinder of 50 plus minus 0.5 millimeters, let's say, a cylindrical pin, a pin which has got diameter 50 millimeters plus minus 0.1 millimeter, let's say. So that has nothing to do with these numbers that you see in this rectangular block. The numbers are basically representing the tolerance zone. And we will just see what we will actually see in a couple of slides later what tolerance zone basically means. But these numbers are not representing the tolerance on the size of the feature. It is basically tolerance. It is the amount of tolerance that you are providing on the location of the axis of the object or the cylinder. Is it making some sense, or it is not, like you are not getting it at all?
It's a little bit confusing.
Okay, I'll try to explain with in the later slide, and I will come back to your question again. And if still it's not clear, please let me know. Okay.
Thank you.
Yeah. So here actually will be more clearer actually. So this is basically the four views of the same drawing, and each one is representing a specific information. So here I have a small cylindrical pin. It basically has got a head as well. So it has a bigger diameter, smaller diameter. The smaller diameter has got a size which is 10 plus minus 0.005. And it has got a GD&T symbol which is representing that this is attached to this line, a projected line here. And it basically says the first compartment show the symbol, and this symbol, if you remember, it is straightness symbol. It represents that this line that you are seeing here, the projected line of the cylindrical feature, this has to be controlled with a straightness of 0.003. So what it basically means that if I draw a line on the top and the bottom, straight lines on the top and the bottom, then what this drawing is saying that I can have out of form, or I can have roughness on this surface, on this line, as long as the two lines are separated by 0.003 units. Does it make sense?
Yes, it makes sense.
Yeah.
Yeah.
Yeah. This rectangular block does not say anything about the size. The size of this cylindrical cylinder or the cylindrical pin has to be between 9.995 to 10.005 as provided by this dimension. So there is no information that is going to be used from this 0.003 specification that is mentioned in this feature frame on the size. The size is controlled by this dimension alone. Nothing is going to change it. This feature frame controls the straightness of this line as shown in this view. That's it. Going to the next view here, the same part, same dimensions, 10 plus minus 0.5. Now A is the datum plane attached to the dimension line. It basically means the datum here is the axis of this pin. Center, the theoretical datum is basically the axis, and that is basically referenced by A. Now I'm looking at this feature frame. This feature frame is attached to the extension line of this view of this edge. And what it says that this face of this cylinder or the head of the pin this face has to be perpendicular. This is the perpendicularity symbol, perpendicular to the axis, which is the datum A, by a tolerance zone of 0.002. So perpendicularity of this face has to be within a tolerance of 0.002. So what it basically means that this straight line can be offset if you follow the mouse. I don't know if I can draw something in there. If you guys can help me with, I was remembering somebody was writing something on the screen using the cursor. I don't know if it can be done or not. But okay, let me see if somebody mentioned something. Annotations, yeah, that's what I need. So how can I use annotations? Yeah, how do you do that?
At the top, it says view options, and there's an annotate button, I think.
Just give me a second. I'm just trying to figure out how to annotate. Okay, yeah, I see here. So what I'm saying that this part this face can be like this, oriented like this, or it can be oriented like this. As long as the separation between these two is 0.002. Does it make sense?
Yeah.
And that goes from the bottom to the top.
Come again, sorry.
So if it goes outside of that 0.002 anywhere on the object, it's not good.
Yeah, it's not basically as per the specification. The same thing was for straightness. So the straightness basically means that it's not perfectly straight. The straightness is that if I have a how to control a straight line, draw a straight line.
There's an option for a straight line, I think, in annotations. You got it.
This one and this one. And this, so what this specification is saying, feature control frame is saying that this edge can basically vary like this. Just give me a second. Anything like this is acceptable as long as it is lying within a straightness is defined by the two lines which are 0.003 millimeters apart. Does it make sense?
Yes.
The same thing will happen for so the same thing will happen for, just give me a second here. So what this third view and the fourth view are basically going to be the same information, giving the same information. What it says that the feature control frame is attached. Feature control frame is attached with the dimensions. Whenever the feature control frame is attached with the dimensions, that means with the datum or the tolerance is defined with respect to the center axis or center plane. So here the feature control frame is attached to the line itself. So basically it controls the tolerance of the straight line or straight edge here. But if the datum or the feature control frame is attached with the dimensions, that means the datum is representing the center axis and the feature control frame is also applicable to the center axis. So here in this third view, view number label C, the dimensions is diameter 10 plus minus 0.005, and it has got a feature control frame which says the axis, because it is attached to the dimension, so this control frame is applicable to the axis of this cylinder. The axis has to be straight with a tolerance of 0.003. That means the axis can lie between two straight lines that are 0.003 millimeters apart. So that you can have a cylinder that will go like this or behave in a different fashion. There can be different curvatures, but as long as it is remaining within these two straight lines, the axis remains within these two straight lines, it is 0.003 millimeters apart, this part will be acceptable to me. Does it make sense?
Yeah.
Yeah. Let me ask you, what is how this drawing D is different from drawing C? What is the difference in these two drawings, C and D? Same, but they are still slight, they are still looks different. So what is the difference? Can you point out a difference? Actually, I agree with you that they provide the same information. Yeah, the arrows inside out and outside, yeah, of course. So what is it is saying that the if you see C and D views, the dimension, the diameter is basically outside, mentioned outside, and the feature control frame is attached to it. So that is one way of representing the GD&T symbol. Another way is that you use the leader line of the dimension itself to attach the feature control frame. So feature control frame is attached to the leader line of the dimension itself. Here, the feature control frame is placed separately, but here it is attached to the dimension itself. But both this C and D are going to convey the same information. Does it make sense, guys?
Yes.
Yeah.
Yeah.
Yeah. Any questions from anybody? Okay. So having done that, let's go to the next slide. How to re-raise these annotations now?
There should be an eraser option in the annotations.
Or an undo, I think.
You're all right. So now coming to the form control in GD&T. So as we actually, as I discussed or described you in the very beginning, that there are different types of symbols. They control the form, orientation, the runouts, and the location control. So we will basically see some of the ways that the part is specified or the GD&T symbols are specified, that amount of tolerance zone and how they are inspected. And you can get more information by going into this reference, as excuse me, as I mentioned in here. So if you're talking about straightness of a line element, just the one that we were seeing in the earlier slide. So if you are basically controlling the straightness of this circular pin on this drawing, it basically means you are using a straight uh, flat plate, which is used as an inspection gauge plate, and you are measuring the deviation from the flatness for the entire line or straightness from the entire line of this curvature. And if there is a tolerance, if there's a deviation from that straightness by this much amount, that means we are within the tolerance. If not, then basically we are outside the tolerance. Does it make sense, guys?
Yes, that makes sense.
Yeah, it does.
Cool. Similarly, straightness of an axis is basically measured by first putting this pin in a V block and then use a dial indicator and rotate this pin, and you will basically see what is the offset that you will have. Or basically for straightness of an axis, you basically go not rotate it, sorry, that will be run out. But for straightness, you will move the dial gauge along the length of this pin, and you will see how much straight the axis is, or basically the true surface of this pin is basically. So that will help you to locate the true axis or to control the straightness of the part. Runout controls. So these are basically most favored controls when we are trying to inspect the cylindricity of an object. So for example, if you want to make sure that this pin has, or this cylindrical object has a perfect form, then what you can do, you can use a dial gauge indicator and first you will actually place this object in a chuck of a lathe machine, and then you rotate the chuck of the lathe machine and you use a dial indicator to measure how much offset, how much readings are you measuring when it actually goes to a complete 360-degree rotation. And that will give you how much offset the profile of the surface is. And if you go measure that throughout the length, that will give you total runout. And if you measure it along at one cross section, that will give you circular runout. So circular runout is basically measured at one cross section. So that basically says that this feature control frame basically mentions that this surface must have a circular runout within tolerance zone of 0.01. So basically means that if I am going to put my dial indicator and going to rotate this object, then I will have the runout of only 0.01 millimeters allowed. And total runout is basically throughout the length, which is measured how much offset you are measuring throughout the length of the object. So that will basically give you total runout of it. Now, I remember there was one question and I mentioned that I will take that later. Can somebody repeat that question? I will try to answer that in this slide. I just slipped from my mind. I just mentioned that I will come back to this question again.
I think that was my question about I forgot exactly what it was, to be honest.
Yeah, so it was probably we are discussing about data feature simulator. So here in this part, if I ask you guys, what is my datum? Looking at this plane A, what is my datum? What is my datum feature simulator? And what is my datum feature? Can you guys help me to answer that? What is my datum? What is my datum feature? And what is my datum feature simulator?
Would the
it would be the spindle. The datum would be the spindle. The datum simulator, or your actual datum surface would be the inside of the jaw.
Yeah, so you are basically getting it correctly here. So when I say datum feature is represented by this symbol A, representing the outer surface of this object, or if I consider that as a part A that has got a cylindrical surface, so that surface, which is a non-ideal surface as you can look at, so that is basically my datum feature A. The datum is actually the center axis of this feature, which is this axis. How to locate that? I will place this part inside the chuck of the lathe machine. The lathe machine is what I'm considering as a feature simulator, and the chuck of that lathe machine, I consider that is perfectly oriented and perfectly centered, and that will be my feature simulator. And if I rotate the chuck, then along with the rotation of the chuck, my part will also rotate. So I will assume that the axis of that chuck will represent a datum axis, theoretical axis. So if my chuck is rotating, so I will assume my part will be rotating along the same axis, concentric axis. So the datum feature is a surface datum axis, theoretical axis, defined by the datum feature simulator, which is the chuck of this lathe machine. Let me know if it makes sense to you guys or not. Are you guys able to get that part?
Yes.
Yeah, it's making sense.
Yeah.
Yeah.
Thanks. Okay, so now we basically move to the profile of a surface. So what is profile of a surface? There is another symbol that we have seen, and it basically is another control, which is basically saying that the profile, which is a contour of a part, must stay within the true contours which are separated by 0.1 tolerance zone when this part is constrained against datum A and datum B. Datum A is the bottom face, datum B is the back face. So when I place this object at the bottom face and put it against the back face, after putting it like this, if I measure the profile of this surface and measure how much offset it is from the true form, then it must have a tolerance of 0.1 millimeters only. So that is what basically the profile tolerance means. Does it make sense to everybody so far?
Yeah, it does.
Great. So with that said, the last part is about the location control. And the location control basically means that if I have to locate a feature, and this location is basically provided by this feature control frame. So I have this drawing which has got the different datums, datum A, datum B, and C is defined. And I have to locate the hole from the base or from this side. So how to locate that? So first we have to find the center, define the true center of this hole. The true center of this hole is defined by the basic dimension, 6 units from the bottom, 2 units from the left side. So those are basically the dimensions representing the theoretical position of the center of the hole. Now they will just be theoretical dimensions. They will not be used as such. They are just used to locate the center of the hole. Now, locating the center of the hole, then we have to define the size, what the size of the hole would be. It will be diameter 1 plus minus 0.1 units, millimeter, let's say. And then on top of that, I have a feature control frame which defines a position tolerance or position tolerance of a amount of cylindrical tolerance zone of 0.15 millimeters when the part is constrained to move against datum A, B, and C in that order. So what it basically means that this feature control frame basically means that the center axis of this hole must lie within the cylindrical tolerance of 0.15 millimeters. So if you look at this part, it has got a bigger cylinder and a smaller cylinder. Smaller cylinder represents a tolerance zone. That means my axis of the hole can vary can be oriented in any angle as long as the axis remains within the cylinder of 0.15 millimeters. Does it make sense to you guys so far?
Yeah. Yeah. So the axis can be I don't know how to, kind of hard to ask, like, to word it. Like the axis can be 0.15. So like 0.15 is your tolerance. So
yeah, the axis.
Like,
okay, so let me
straight, right? Like it can turn diagonally, but as long as it stays within that 0.15.
Yes. So let me actually explain. So what it basically means, I would assume this cylindrical hole should be perpendicular to datum A, right? The back face should be as perpendicular as possible. The axis should be perpendicular theoretically, right?
Yeah.
But if I provide this tolerance zone, the axis basically can also be away from perpendicular. It need not be perpendicular to datum A. It can basically orient like this. So if I use my annotations as you just showed me again, so the axis can actually lie like this, or the axis can lie like this, as long as it remains within the cylindrical tolerance of 0.15 millimeter as shown here.
Okay. Yeah, sounds good.
Axis need not be perpendicular. Axis can be like this. So my hole in that case would be like this. My hole would, in exaggerated form, my hole would look like this if my axis is like that. It's in exaggerated form. Exaggerated, it is not like that big jump in or deviation, but what it says that if my axis is like this, the hole would be like drilled like this, and it will be perfectly acceptable as long as the axis is within the cylindrical tolerance of 0.15 millimeters. Yeah.
Yeah, perfect. Thank you.
Great. Good. Any questions from any other students in the class? Okay, so if not, then I think we come to this topic about bonus tolerances, and hopefully, let me see how many slides are still remaining. Okay, so I believe that is the last slide that is of importance that we need to be focus on, and thereafter we'll wrap our class today. And in the next lecture, what I will do, I will try to take some few examples for GD&T drawings and try to see if we can practice some of the symbols and specifications with you guys in the next lecture. Does it make sense, everybody, so far?
Yeah.
Yeah, it does.
Okay, great. So this is the last topic to focus on. And I mean, last topic means we need to understand what is mean by bonus tolerance. So here we have a specification of a drawing. Or a drawing, we basically have the part that has got a cylindrical boss, which is projected outwards. And this is a hole that has got, and that is drilled inside this plate. And we have got a size of the cylindrical boss, the extruded part, and the size for the hole as well. And both these cylinders have a feature control frame as provided by these rectangular blocks. Everything else in this drawings, you already can figure it out, whether it is this length or this dimension, size, this size dimension, datum C here, datum B here, and datum A at the back. So everything else you actually can figure out. These are the basic dimensions: 100 from the bottom, 50 from the left hand side, similarly 170 from the bottom, and 50 from the left hand side. Theoretical dimensions to locate the center, theoretical center of the hole itself. So everything else you can figure it out here, and I'm sure you can figure out the information in this feature control frame as well. Now, what we are learning here is that many times we will see that as a designer, if we can provide some tolerances and in the drawing, and if the tolerances are fixed tolerances, then the manufacturer has to manufacture the part within that fixed tolerances. But if we are as a designer, we are comfortable with some additional tolerances depending on the functionality of the part, then this specification, as we will see now, will provide additional tolerances to the manufacturer. How? Let's see what it basically means. This is a cylindrical boss, which is extruded part. It has got a dimension of 50 to 50.3. So if I ask you guys, what will be the MMC condition for this cylindrical boss? What will be the diameter that corresponds to MMC condition? Is it 50 millimeters or 50.3 millimeters? At what dimension?
50.
Most amount of material. Sorry?
It would be 50.
50. Just see whether it is 50.
Oh, it's an extruded feature. It'd be 50.3.
Perfect. It will be 50.3, as somebody also mentioned in the chat window. Yes, it will be 50.3, because at that time or that point, you will have maximum material condition in that feature. Now, this feature control frame says that I will have a position tolerance on the axis of this extruded part within a cylindrical tolerance zone of 0.2 millimeters when the part is fabricated at its MMC. That means when the part dimension is 50.3, then my tolerance zone for the axis is 0.2 millimeters. That is what it says. But if I fabricate my part by 50.2, then I basically have 0.1 millimeter as an additional tolerance that gets added to my tolerance zone. So this 0.1, which is basically an offset from my MMC, that will be added to tolerance zone, and that means the tolerance zone becomes 0.3 millimeters. Similarly, if I am fabricating the part at 50.1 millimeters, then I will have a bonus tolerance of 0.2 millimeters that will be added to the actual tolerance zone. So my tolerance zone will now become 0.4 millimeters. And similarly, if I'm fabricating the part with 50 millimeters, my actual tolerance zone will become 0.5 millimeters. So that is the bonus tolerance that is available to the manufacturer that this drawing is specifying. Does it make sense to you guys?
Professor, so the max tolerance goes out to 50.5?
No. So here you see that this dimension has nothing to do with the size dimension. You cannot add this number with these numbers. This number on the rectangular frame represents the dimension of the tolerance zone. If I actually, okay, use my annotation again, just give me a second. So what it basically says that the axis of the cylinder is lying within 0.2 millimeters, right?
Yes.
That's what it is saying. And the diameter is varying from 50 to 50.3. The diameter cannot go beyond 50.3 and cannot be less than 50. But if I am manufacturing this external diameter at 50 millimeters, then that means the tolerance zone I am having is 0.2 plus 0.3, which is mean my tolerance zone will be bigger for my axis. My axis can now can be more inclined to the actual surface. So it need not be perpendicular to the back surface. It can be more inclined. So that is the extra tolerance you are adding on the orientation of the axis. You are not changing the dimension of the extruded part. You are just adding the tolerance on the orientation of the axis itself.
How do you measure the orientation of the axis?
How to measure the orientation of the axis? So as I actually mentioned to you before, so cylindrical object is basically used as in is either using the chuck of the lathe machine or the spindle or chuck of a simple spindle that is basically going to the datum feature simulator. That will help you to measure the perpendicularity of the object.
Okay.
Yeah. So if you insert a gauge pin, so if it is if it is an external part, then you will use actual mating envelope. If we remember, we discussed about the actual mating envelope part. So if you use a hole which a gauge block that has got a hole of this diameter and try to fit with respect to the bottom face A, that will provide you the perpendicularity or control the perpendicularity of this feature itself or the axis itself. I'm not sure if I'm making sense here, but let's discuss about it in detail more about in the next lecture about how to measure that axis orientation of the axis itself. Okay.
Okay.
Yeah. But anyways, about the bonus tolerance, is everything making sense to you guys so far about the bonus tolerance?
Yeah, everything makes sense.
Yeah.
Same thing when we have this incoming feature, you basically have the MMC at 30 millimeters. So at that time, the bonus tolerance is 0. But when I actually fabricate it for 30.3, then the 0.3 will be the bonus tolerance that gets added to tolerance zone. This 0.3 is basically added to tolerance zone because 0.5. So it is not 30.5 is not the acceptable dimension because I'm not adding 30 with 0.5 here. So these are the size, acceptable sizes. These are the acceptable tolerance zone corresponding to the sizes that are getting fabricated. If I fabricated 30 millimeters, that my tolerance zone is 0.2 millimeters. If I am having my hole at 30.3 millimeters, then my tolerance zone is 0.5 millimeters. Tolerance zone basically means the zone on which my orientation of the axis will lie. Let me know if you guys have any questions on this so far. Okay, so having said that, if there are no questions, then so the next part is how to interpret. I think we actually covered this as well in the last lecture, that how to interpret a GD&T drawing. By now, I believe you know everything that this drawing or this drawing is conveying. Whatever information or whatever symbols are used in this drawing, I am sure that you guys now understand it. So if you do not understand it, please have a look at it and let me know which part you are not understanding and try to explain that part again. Please have a look at this drawing all the symbols, all the dimensions, and let me know if something is not making sense to you.
Just to make sure I have this like understood properly, if the circle, like the inner diameter was and they manufactured it to be exactly 1.000, would the bonus tolerance be 0.005?
Yes, you are right. And why is it? Because this is an internal feature. It has got an MMC at 1. No, it will not be 0.005, sorry. It will be 0.003 because at MMC, the MMC is at 1, right? For internal feature. At MMC, this is the tolerance zone. But when I am away from my MMC, which is when I am 1.002, then it will be 0.005. Let me
okay.
tolerance zone again. This is the internal feature, 30 to 30.3. The MMC happens at 30. So when the material is at MMC, then I have no bonus tolerances. Tolerance will be as specified in the drawing, which is point. But when I'm away from MMC, which I am basically 30.3, then that extra 0.3 gets added to the tolerance.
Okay, I got it. I had it backwards from the external and internal feature.
Yeah. Is everybody getting this part so far?
Yeah.
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 Yeah, makes sense.
So where is datum B? So datum A is the back surface. Datum B is attached to this feature control frame, which is basically the side face. Side face, which has to be perpendicular to datum A. So one of the side faces is datum B, and the bottom face is datum C. So back face is datum. If you look at this view, the back face is datum A, the side face is datum B, and datum C is the bottom face. Okay.
Professor.
Yeah.
So you would attach it to the datum A first, then B,
Yes.
then C?
Yes,
then
yes. That is the order of the datum specified. So whenever we are measuring this, inspecting this, or finding the measurement of how much the axis is away from its perpendicularity, or how much it is not out of its form, we are first immobilizing or constraining this part against the surface plates of back. First we're resting against the back surface, then we are resting against the side face, and then we are resting against the bottom face. So these are the order of datums that needs to be satisfied while doing the inspection. So let me know if there are any other questions, guys.
I have one.
Yes, go ahead.
Is this how you want our engineering drawings to be for our projects?
Okay, so yes, but that will be your homework number 1. I don't want you to have the drawings like this for your project, but your homework number 1 I will be posting it soon, and it will be just to use one of the part from your project and use all the GD&T techniques that you have learned to control the form, orientation, location, and size of that part in the drawing. So you have to basically create your own drawing and submit it as a homework. Okay, does it make sense?
When you say all of them, do you mean like every single one, or just the ones you need to manufacture?
Yeah, just the one that you think is needed.
Got it.
Yeah. Great. So if you guys understand every single details that are there in the drawing, that means you know how to interpret GD&T by looking at any drawing from now onwards. Now, the same steps are to be followed when you are implementing, or when you are going to introduce the GD&T symbols in your drawing. So you have to select the datum features, control them. Control basically means flatness, perpendicularity. You have to control that to locate the features. So if this is a feature, it needs location dimensions. You locate the features. You then size and locate the features of size. So feature of size has to be given proper dimension and tolerances. And you refine the orientation and form if needed. So this form and orientation is required to be controlled. So you give another feature control frame and GDNT symbol. So these are some basic steps that you provide or that you use to implement GDNT. The last slide is that when to use and when not to use GDNT. So if you see here that depending on the amount of tolerances, the percentage increase in the cost is like exponentially. So if you keep on increasing the tolerances, the type of machining process will actually gets changed depending on what type of tolerances you need. And depending on that, your cost of the fabrication will actually increase. So the guideline is that the tolerance should be as generous as possible without interfering with the part functionality to minimize production costs. So to minimize the production cost, you need to have higher tolerances, but at the same time, as a designer, you have to make sure that the part is going to be functional or not. So that is the last message of this lecture, that just because now maybe in a couple of lectures and couple of weeks you will be like knowing all the GD&T symbols and drawings. So that does not mean that you have to use those symbols in any drawing that you're going to fabricate or use, because when you are going to introduce GD&T symbols, that is going to have a cost associated with it. So you have to make sure that you are going to introduce GD&T in a drawing only if it is needed for the functionality of the part. If you think just by providing the coordinate dimensioning style will help you to get the part which will be functional, just stick to that, because even in that case, rule number 1 of GD&T still applies, which says perfect form at MMC. So even if you do not provide any GD&T symbol, the ASME standard says that it should have perfect form at MMC. So that still apply. So if your part is functional without any extra GD&T symbol, do not use that. But if you really need to control the form and orientation, you know you have the tools available to you and you can use that in your drawings. Is that making sense to everybody so far?
Yes.
Yeah.
Yeah. Any questions from anyone? So if not, then let's wrap up today's lecture then, and I will see some of you guys tomorrow in the lab session. Thank you.